To calculate the circular mil, or Cmil, of a cable for a looped system, it is important to understand the formula and its components. The formula is Cmil equals 2 multiplied by the distance to the load in feet multiplied by the amperage multiplied by K, all divided by the maximum voltage drop. Let's break down each component. Firstly, the distance to load is the distance from the power source to the load, measured in feet. In a looped system, remember to use the distance to the furthest load point from the source along the loop. Secondly, amperage represents the maximum current that will flow through the cable, measured in amps. This is determined by the load requirements of the system. You should use the maximum anticipated current plus a safety factor. Thirdly, K is a constant that depends on the type of cable being used. For copper conductors, a common value for K is approximately 12.0. However, it is crucial to verify this value based on the specific cable manufacturer's data and the relevant electrical codes. Fourthly, the maximum voltage drop is the maximum allowable voltage drop in volts, as specified by electrical codes and design requirements. This value ensures that the equipment connected to the system receives adequate voltage for proper operation. Now let's consider an example to illustrate the calculation process. Suppose we have a looped system with a distance to the load of 6,560 feet, a maximum current of 393.65 amps, and we are using a copper conductor with a K value of 12.0. The maximum allowable voltage drop is 275 volts. Plugging these values into the formula, we get Cmil equals 2 multiplied by 6,560 multiplied by 393.65 multiplied by 12.0, all divided by 275. Calculating this gives us a Cmil value of approximately 115,068.93. Therefore, based on these parameters, the cable should have a circular mil area of at least 115,068.93 Cmils. It's important to note some common errors that can occur during this calculation. Firstly, using the incorrect value for the constant K. Always refer to the cable manufacturer's specifications and applicable electrical codes to obtain the correct K value for the specific cable being used. Secondly, using the incorrect distance to the load. Ensure that you are using the accurate distance from the power source to the load in feet, especially in loop systems where the distance may not be a straight line. Thirdly, using inconsistent units. Ensure that all values are in the correct units, such as feet for distance, amps for current, and volts for voltage drop, to avoid errors in the calculation. Now let's discuss some additional considerations for cable sizing. One consideration is ampacity. Ampacity refers to the current carrying capacity of a conductor, and it's crucial to select a cable with an ampacity rating that meets or exceeds the calculated current requirements of the system. Electrical codes such as the National Electrical Code, or NEC, provide tables and guidelines for determining ampacity based on conductor size, insulation type, and installation conditions. Another consideration is voltage drop. Excessive voltage drop can lead to equipment malfunction, reduced efficiency, and potential safety hazards. It's important to limit voltage drop to acceptable levels, typically 3% for branch circuits and 5% for feeders, as recommended by electrical codes. The Cmil calculation helps ensure that the selected cable size minimizes voltage drop within these limits. Next, consider environmental factors. Environmental conditions such as ambient temperature, moisture, and exposure to chemicals can affect cable performance and longevity. Select cables that are suitable for the specific environmental conditions of the installation location, considering factors such as temperature rating, insulation type, and resistance to corrosion. Lastly, consider future expansion. Anticipate future load growth and expansion when sizing cables for electrical systems. Oversizing cables slightly can provide additional capacity for future needs, reducing the likelihood of costly upgrades or replacements later on. Remember, always consult with qualified electrical engineers and adhere to applicable electrical codes and standards when designing and installing electrical systems. Accurate cable sizing is essential for ensuring the safe, reliable, and efficient operation of electrical equipment and infrastructure. To recap, Calculating the Cmil involves understanding the formula, accurately determining the distance to the load, the maximum amperage, the K constant, and the maximum voltage drop. Avoid common errors such as using incorrect K values or distances. Also consider ampacity, environmental factors, and future expansion plans when selecting cable sizes. Remember to consult with qualified professionals and adhere to all applicable electrical codes and standards to ensure the safety and reliability of your electrical systems. To further elaborate on the importance of each component within the Cmil calculation, let's delve into more detail. Firstly, the distance to the load is not merely a physical measurement, but rather a critical factor influencing voltage drop. In a loop system, the current divides and flows through multiple paths to reach the load. Therefore, it's essential to consider the longest path, as this will experience the greatest voltage drop. The distance should be accurately measured, taking into account any bends, turns, or obstacles in the cable route. Errors in distance measurement can lead to significant inaccuracies in the Cmil calculation and subsequent cable selection. Secondly, the amperage is not simply the sum of all connected loads, but rather the maximum anticipated current that the cable will carry under normal operating conditions. This includes consideration of motor starting currents, harmonic currents, and any other factors that may increase the current flow. It's important to use appropriate demand factors and diversity factors to accurately estimate the maximum current demand. Underestimating the amperage can result in cable overheating, insulation failure, and potential fire hazards. Thirdly, the K constant is not a fixed value, but rather a variable that depends on the specific properties of the cable conductor material and insulation type. Different materials have different resistivities, which affect the amount of voltage drop for a given current and distance. Copper and aluminum are common conductor materials, each with its own K value. Additionally, different insulation types have different temperature ratings, which affect the cable's ampacity and voltage drop characteristics. Always refer to the cable manufacturer's datasheets to obtain the correct K value for the specific cable being used. Fourthly, the maximum voltage drop is not an arbitrary value, but rather a performance criterion that ensures proper operation of connected equipment. Electrical codes typically specify maximum allowable voltage drop limits for different types of circuits and equipment. Exceeding these limits can result in reduced equipment efficiency, dimming lights, motor stalling, and other performance issues. It's important to design the electrical system to maintain voltage drop within acceptable limits under all operating conditions. Now, let's consider some additional factors that may influence cable sizing decisions. One factor is the type of load being served. Different types of loads have different voltage requirements and sensitivity to voltage variations. For example, sensitive electronic equipment may require tighter voltage regulation than lighting or heating loads. It's important to consider the specific requirements of the connected equipment when selecting cable sizes. Another factor is the installation method. The way in which the cable is installed can affect its ampacity and heat dissipation characteristics. Cables installed in conduit, underground, or in free air will have different ampacity ratings. It's important to follow the installation guidelines provided by electrical codes and cable manufacturers to ensure proper cable cooling and prevent overheating. Furthermore, consider the effects of harmonics. Nonlinear loads such as electronic ballasts, variable frequency drives, and switch mode power supplies can generate harmonic currents, which can increase the overall current flow in the cable and increase voltage drop. It's important to analyze the harmonic content of the load and select cables that are adequately sized to handle the harmonic currents. Also, think about deterring factors. Deterring factors are used to reduce the ampacity of cables under certain conditions, such as high ambient temperatures, multiple cables in a conduit, or underground burial. It's important to apply appropriate deterring factors to ensure that the cable is not overloaded and operates within its temperature rating. To ensure accurate and reliable cable sizing calculations, it's recommended to use specialized software tools and consult with experienced electrical engineers. These tools can automate the calculation process, taking into account all relevant factors and deterring factors. Additionally, Electrical engineers can provide valuable insights and expertise in designing electrical systems that meet all applicable codes and standards. In summary, calculating the Cmil of a cable involves understanding the formula, accurately determining the input parameters, and considering various factors that may influence cable sizing decisions. By paying attention to detail and consulting with qualified professionals, you can ensure that your electrical systems are safe, reliable, and efficient. It is also important to remember that the electrical codes and standards are constantly evolving, so it's important to stay up to date with the latest requirements. The National Electrical Code, or NEC, is the most widely adopted electrical code in the United States, and it's updated every 3 years. Additionally, other countries and regions may have their own electrical codes and standards that must be followed.